have Ellen Saada as our guest from University of Paris. She's going to talk about ergodicity for some dynamics of DNA sequences. Ellen, the floor is yours. You can start when you want. Thanks for accepting the invitation.
Okay, so thank you for the invitation. I like this seminar very much, and I try to follow it as much as possible. So I will speak of a joint work with Michael Falconnet and Nina Gantert. We've done some time ago, but we didn't really speak about it. So the point is to understand a model for the dynamics of DNA sequences, and it will be modeled by particle systems. So we'll first explain the model and the questions we have, and then the framework of the model within particle systems, the results we have, what is related in more classical examples, and if I have time, more proofs. Okay, so for DNA, you know that there is an alphabet of 4 letters, A, T, C, G. For adenine, I'm not sure about the pronunciation in English, adenine, thymine, cytosine, and guanine. And it's composed of 2 different types of nucleotides, purines, R, which is AG, and pyrimidines, which is Y, which is CT. And we will denote XPZ if we have denucleated with the first one in X and the second one in Z. And so we have an infinite sequence, and we want to know how it changes. So for the usual models, it has been the evolution of independent of the sites according to a Markovian kernel. So there is a finite sequence, configuration eta in A to the power n, and everything is independent. So the famous example is the Jukes and Cantor model. So you get the product of NIID continuous time Markov chains, and they model single site nucleotide substitutions, and all substitutions occur at the same rate. But then what it implies is that there is convergence in law and of the sequence to a unique product stationary measure. But this is not very realistic, because it's well known that, for instance, the denucleotide CpG is less frequently present than would be expected in some independent model. So, for instance, to go from C to T is much more present when C is in denucleated CpG. So there have been more realistic models at the beginning of the 2000, and something like Jukes Cantor model plus CpG effect. So there is an additional rate to model these neighboring effects. So that's what we are interested in. So we'll look at a model which is called RN+YpR, which is a generalization of GC plus CpG and other models. And it was introduced by Berard, Guéret, and Pio and studied by them. And so what is this model? So as I said, there is the independent evolution side by side plus some rates to model the neighboring effects. So first, for the independent part, the rules are that for every pair of nucleotides X and Y to go from X to Y, it may depend on X, but only through the fact that X belongs to R or that X belongs to Y. So it means that if we want to go from C to A or from T to A, it must have the same rate, and also from A to C and from G to C and so on. And then there are 4 remaining rates which correspond to be within the same class, to go from R to R or from Y to I, and then Y to Y, and then it's independent, it's free. So here is the matrix. So you see there that, for instance, to go to A from T and from C, it's the same rate V. Then you have the free thing, which is to go from G to H W, but to go from A to G, it's WG, so it's different values. And we assume that V is less than W, could be equal. And then we have this additional rate for YpR. So if we have denucleated in belonging to YpR, like CG, CA, TG, and TA, then what happens is that there is an additional rate. For instance, if we have CG, then it could move to CA. So it means that G moves to A, but to its left, it has C. So there's this additional rate that we denote by RAC. A, that's where you go, and C is the other nucleotide on the left. Or from CG, we could go to TG. So C goes to T, but looks at G on the right. So the rate we denoted by RTG. So you see there are many, many rates, more R. And then there are some, okay, so this RN plus YpR is theoretical model. It doesn't correspond to any biological setup, really. It's just a model with a huge amount of parameters. And something more real, okay, which exists, it's something called the RNC plus YpR. So then it's also something in the middle, not really a biological model, but then you have some rates which are equal. For instance, WA is equal to WT and so on. Then we go to more classical model like the T92 plus CPG. So then you also have equal values. And here in the R, you see that there are only two values that are different from 0, equal to R, and then 0 everywhere. And the GC plus CPG I spoke about at the beginning, here we have only one value, and here 0, 0, and two values with R. So what Berard, Guéret, and Pio proved is the fact that if the minimal of the V's is positive, then the dynamics is ergodic in the sense of particle systems, meaning that there is exactly one invariant probability measure, and for each starting point, there is convergence to this measure. So they did look at an infinite series, something on Z. Okay, we're also interested in the fact that the process could be exponentially ergodic. So meaning that for any initial probability measure, we would have the integral of f d nu st, which converges to integral of f d mu bounded by a1, a minus a2t, with a1 depending on the function f. And okay, so that's for substitution. But what we are interested in is the fact that it's not, we don't have only substitution in the DNA, there are also insertion and deletion of nucleotides. So we wanted to model this. It's a little complicated to do insertion, deletions, and put together. So we did something which is at the same time insertion and deletion, and we modeled it by cyclic permutations, and we call this a cut and paste process. And this is also something that exists in the biological literature. And so we are interested in the ergodicity of the superposition of substitution and cut and paste. Okay, so we will put all this in a particle system framework. So our state space will be x a to the z, so it's one-dimensional model. A is our alphabet ACGT. In general, it could be some finite alphabet. So a substitution process, we have one coordinate which changes at each transition. And for instance, if eta is the configuration, at eta x it goes to A, and we denote it by eta AX. And the rate will be CXA eta. We want this rate to be translation invariant. We'll write CA eta for when x is equal to 0. And we'll assume that it's finite range. It means that going to A depends through a finite set, which depends on this value A. And so we have the generator of this substitution process, which write like this, as usual way. And we'll denote by K the maximal rate, by S the maximal range of interaction. And we'll assume that K and S are finite, which will be the case in our model, to have the model exists. And we also assume that the infimum of the rates will be positive. Okay, so this is just to summarize for our Rn plus YpR, all these values. So for instance, what is the rate to become A? So as I said before, there are three cases. Either, so for 0 to become A, either eta 0 belongs to the set Y, then okay, it's the value VA, or eta 0 belongs to the set R like A, so it means that eta 0 is equal to J, and then we are in this YpR situation. So we have to look on the left to look at the Y value. So either eta -1 on site -1 is not a C or a T, and then the rate is W, or it is either C or T, and then we have WA plus this additional rate RA alpha. And so here the dependence, the range is -1, 0, so we have a range 2. And okay, all the other cases are the same. And so here you see that the maximal rate is the maximum of the W plus R, WA plus RAB and B for A in Y and B in R, that the minimum value is the minimum of the V's, and that S, the maximal range, is 2. Okay, so we looked at the substitution, then we look at cut and paste. So transition are, as I told you, circular permutations of finitely many sites. And there is a probability matrix P, which represents the rate at which the coordinate eta x is transferred to a site Y. We assume that P is translation invariant, but we do not assume that P is symmetric. So that's the way things move with this cut and paste process. So we denote by sigma xy of eta the fact that eta x goes to site Y. So it could be to the right or to the left, like this. So that's this sigma xy. And so this is the generator of this cut and paste model. So pxy here gives the rate of change from eta to sigma xy eta. We assume this so that the dynamics exists. And actually, I didn't mention that it's not symmetric because this type of permutations of cyclic permutations, it was studied by Kovshekov in a paper where he studied the invariant measures of finite range permutations as a generalization of exclusion, but he considered the symmetric P. Okay, so our goal is to superpose the two dynamics. So we have a constant rho, and we will look at the generator of the superposition. So LF will be L1F plus rho times L2F. And we want to know if this superposition will or will not be ergodic and for what conditions. So this is not a new question to look at this superposition. And why is it interesting in our case? It's interesting because we know by Berard, Guéret, and Pio that the substitution process is ergodic. So we have superposition of an ergodic dynamics and another one which is not ergodic. So what can we say of the superposition? And this is reminiscent of the positive rates conjecture, which was, okay, many people worked on it in the 90s, I think 80s or 90s. And this was done for one-dimensional spin systems with values in 0, 1. And it's not general. I mean, it was proven that in the nearest neighbor attractive case, if the minimal rate is positive, then the superposition, then the dynamics is ergodic. And so that's a famous problem in Liggett's book. Prove that a finite range attractive one-dimensional translation invariant spin system with strictly positive rates is ergodic. And okay, that's all. I mean, maybe you know about recent advances on this conjecture. Okay, so let's go to our model. So what we could show is that this superposition is ergodic for a certain range of parameters. You remember we have many, many parameters, V's, W's, and R's. But we suspect that we couldn't find anything that it holds for much more than what we found, and maybe it holds for all the parameters. We don't know. We couldn't get any counterexample. So what we could do is to prove ergodicity in the case of the Jukes-Cantor model plus CPG effect, and T92 plus CPG, and of some of the R and C plus YpR. So here there are more more parameters. And we did follow two approaches to prove this ergodicity. First, we tried duality, and then we tried attractiveness. So I will explain to you these two approaches. If I have time, give some of the proofs. So what's interesting, I mean, what's funny is that it looks very simple, but in fact, it's very, very tricky. So, okay, first duality. So if you have two first the definition, well-known definition, if you have eta t and zeta t Markov processes with two state spaces, and you denote h of eta zeta a bounded measurable function on x times y, we say that the processes eta t and zeta t are dual to one another with respect to this function h, if for all eta and zeta, you have the expectation of the first process eta t, expectation beginning from eta of h of eta t zeta, which is the expectation for the second process, expectation beginning from zeta of h of eta and zeta t. So that's the well-known duality. And in fact, what we'll do is not exactly this. We will follow, generalizing an old paper by Pablo, Ergodicity for spin systems with stirring. And so the idea is to construct a graphical representation of the evolution, then study a reverse time process. But the point is that that's what is done in the usual duality theory. But here it will be a generalized dual because it will not be Markovian. I mean, this generalized dual idea, Pablo says it comes from the famous paper, De Masi, Ferrari, Leibovitz. And okay, and then we could conclude because even if it's not Markovian, it's dominated by a branching process. So I will not give too many. Okay, if I have time, I'll explain the constructions. And okay, so what results do we get? So if you remember that M is the minimal rate, K the maximal rate, the maximal range is S, then the first generalization of Pablo's paper is to say that if we have M positive and S minus 1 times K minus M less than the number of values A of A times M, then we have a superposition which is exponentially ergodic for any value of rho. It is ergodic if the second inequality is an equality. We could do better than that, but it will involve too many notations, so just give this result. And what it gives for our system, so we, okay, working a little more, it's possible to prove that our model is exponentially ergodic with the condition, okay, mean VA positive, that is just M positive, same value. And then another inequality, which involves the rates R, all the rates R less than the sum of the V's. So if you remember before, we had on the right, A times M. So the sum is for this capital A, and M was the minimal rate. And here you see we have the sum of the V's. And you see that there is no W. So this is the little improvement we have. And so it gives for this RN+C plus YpR, okay, a complicated inequality again. And for the simplest model, T92 plus CPG, it gives R less than 2V. And for GC plus CPG, it gives R less than 4V. And so looking at this, we know that it's not good because with attractiveness, we'll see that for those two models, there are no conditions. Okay, so let's go to attractiveness. So okay, first things are quite, so our first, before, are there any questions on this or not? Because I don't see you, so I don't know. No questions.
I think we're fine, yes.
Okay. So attractiveness first, let me just remind things that everyone knows. If we have a total order on our set of values, we write it 1, 2, 3, 4 for the moment. It induces a partial order on the state space, which is the coordinate-wise order. And then if we consider the non-decreasing functions, this partial order on X induces a stochastic order on the probability. We say that mu is less than nu if for any f in M we have mu of f less than nu of f. And then there is an equivalence for the process with semigroup S of t between the fact that if f belongs to M, then S the Tf also for any t, and that if mu is less than nu, then mu st will be less than nu st for any t. Then we have attractiveness. And the way to prove this, okay, the most common is through coupling, and the most common one is basic coupling, meaning that we have a couple of processes eta t xi t. Each one is the initial process, and they move together as much as possible. And then with that, I can prove if it's attractive that if eta 0 is less than xi 0, then eta t will be less than xi t almost surely. Okay, so if we have some attractive process, we know that there are two special extremal invariant probability measures, the upper invariant measure and the lower invariant measure. And for us, the lower one will be the limit of delta 1 times st. So delta 1 will be the Dirac measure on eta with the smallest value everywhere, which is 1. And the mu upper would be the limit of delta 4 st. 4 is the largest value. And we know these measures are translation invariant because our dynamics is translation invariant. And you know that they satisfy that mu L is less than mu U, and any invariant measure is between those two. And to prove ergodicity, we have to prove that those two extremal measures are equal. Okay, so we need to define some order on our set A, and we'll take from now on the order CTAG. It's not the only one, there are many possibilities, but what we could prove is that what we need for an order to be valid, I mean to be helpful, we cannot separate the values in Y and R. So you see here, you have C close to T and A close to G. So to prove our first result, I mean, we did generalize a very simple result in the case of set of two values, which uses Strasson's theorem for coupling. It's the fact that if you have a Markov process which is attractive with respect to some order, so let's take this order, then if any invariant and translation invariant measure satisfy that mu of A is of the value A is equal to the mu of eta 0 equal T, and mu of eta 0 equals C is equal to mu of eta 0 equal G, then the process is ergodic. So you see that AT are in the middle here, and that here in the middle, and that CG are the extreme here. Okay, so how do you get? I'm sure that everyone of you knows this. I mean, okay, Strasson's theorem just saying that you have two measures, then a sufficient, necessary and sufficient condition to have mu1 less than mu2 is the existence of a monotone coupling measure, which is marginals mu1 and mu2, and which concentrates on ordered configuration such that eta is less than xi. And what's interesting for us is the following corollary, which is the fact that if x has two values, and we have the partial order eta less than xi, if we have mu1, mu2, which are such that mu1 is less than mu2, and if mu1 of 1 is equal to mu2 of 1 for any x, then mu1 is equal to mu2. So that's very, very, I mean, kind of strange result. You can get it for the first time, but very simple proof. So we take a coupling measure for mu1 and mu2, and then we just compute the probability to have eta x0 and zeta x equal 1. What does it mean? It means that it's to have 1 for zeta and not to have 1, 1 for eta zeta. But to have 1 for zeta is just the marginal mu2. And here, if we have 1 for eta, because eta is less than xi and mu is concentrating on ordered configuration, we don't need to write that zeta is equal to 1. So it's just minus mu1 of 1. and so it's 0. So very simple proof. And so what we did was to generalize this to 4 values. And so if we want then to apply it to our model, we did prove, okay, first we have to prove that our model for substitution is attractive. So how do we prove this? We did prove that under these conditions, the model is attractive. So looking at, we have to look at substitution to prove that with substitution it's attractive. So it's very simple. You just look at basic coupling between the values, and then what we have to do is to forbid the transition that lead to non-ordered configurations. So for instance, if we take on one side the value A for eta and A for zeta, then what could we obtain? We could do the same thing for both and go to TT with the rate VT, because then it doesn't depend on the neighbors, or CC with rate VC, doesn't depend on the neighbors. But if we want to go to GG, then we are in this YpR setting. So the rates is more complicated because it depends on the neighbor. So here the rate would be the minimal value between CG eta and CG psi. And then we just have what's remaining to get on one side AG and GA. So for AG, it's CG psi minus the minimum, and here it's CG eta minus the minimum. But if eta is less than psi, it's okay to have A less than G, but we don't want GA here. So we want this rate to be 0. Here we do the same. And we also want this rate to be 0. So this just gives, okay, if we put this, then we enter the rates and we get these 2 conditions. And same thing to get the others. And also we know that if the substitution model is attractive, then superposition with cut and paste is also attractive, because cut and paste is attractive. And if we do basic coupling on both, just have addition of 2 attractive dynamics, so it will be attractive. So then once it's attractive, we want to apply our proposition from before. So we need the first moments. And in fact, it's just a computation. We get the first moments as a function of values the second moment, but we don't need these values, in fact. I mean, this can stay like this, and we can compute the values and prove the 2 equalities we're interested in. And so what we get is that the GC plus CPG and T92 plus CPG are attractive and ergodic. And then there are more complicated cases where we have all the rates, all the values of the parameters. So to deal with them, okay, so first there is something which is lighter than the previous one. So in our model, still with our relation C less than T less than A less than J, we can prove that thanks to the first moments computation, that if mu L and mu U, they satisfy both satisfy either of the 2 conditions, then it's ergodic. We don't need both, which is interesting because the relation we had before, this one, it imposes that mu of Y is equal to mu of R and 1/2. So we can imagine that it's too restrictive. And with this proof, with this result, we could have mu of Y different from mu of R. And then we could do more computations with the generator. So this is really, we could just a lot of smart computations, and then get other conditions to get attractiveness. But you see that here we need some rates to be 0. So, okay, so we need rates to be 0. So we could also have rates that are non-zero. So you see the point is that with attractiveness, we can get much better results, but it imposes conditions here. So it's not Okay, there are models without those conditions. So what could we do? And also what we did to get those conditions, we did consider other orders than just CTIG. As I told you, there are other possibilities. So we did consider the other possibilities also. Okay, so that's all. So if I go to more, so why did we ask these questions? I mean, these questions we could look at, for instance, something more classical like stochastic Ising model. And if we have in one dimension, and if you have the rates for this model to be Cx eta is e minus 2 beta with, if eta x minus 1 is eta x plus 1, e 2 beta, if eta x is different from x minus 1, which is equal to x plus 1 and 1. Other than that, for beta, the inverse temperature. We know that this model is ergodic for any value of beta. Okay, but then what happens if we superpose it to cut and paste or even stirring dynamics? Then it will work, but only if beta is small enough. So that's also the same paper of Pablo, or another result by Claudia and Hauser, considering some perturbation type results. And then what else if beta in other cases? So this is kind of open question. And another example, well-known example, is the contact process. So it models the spread of an infection. So eta 0, x equals 0 means that it's healthy site, and 1 it's infected site. So there is a propagation of infection from one side to the others at a rate lambda. And so Cx eta is lambda eta x minus 1 plus eta x plus 1 if eta x is equal to 0. And if you are infected, you can become healthy at rate 1. Then what do we know? I mean, well known that there is a critical value, which is positive and finite, such that the contact process is ergodic if lambda is less than this lambda c. But then again, imagine that we superpose the cut and paste dynamics. What will happen with the rate? There is this value rho, and we know that for each row there will be a critical value, such that there will be ergodicity below that value and non-ergodicity above that value. But the interesting question is, how does this lambda critical of rho depend on rho? There is this conjecture, which was book by Norio Kono long time ago, saying that if 0 is less than rho 1 less than rho 2, we have that lambda c of rho 2 is less than lambda c of rho 1 less than lambda c. Okay, we don't know. It seems that it's still open. It's possible to prove some results, but never these inequalities. And okay, and that's it. So if there is some more time, I could explain to you the graphical representation for duality. Okay.
Yes, Ellen, sorry, just one question. The conjecture that you just mentioned is for which dimension? Any or one?
Let's take one. Even one.
Even one is not.
No.
Okay. Thanks.
And okay, so I wanted to finish with the graphical representation and generalized dual. So to do it, so as I said, we were inspired by what Pablo did in his paper. So we have the rates. This is Ci eta is the rate to become A, side 0. And so we have to write it taking into account all the different cases I mentioned to you. If you are in Y, in R, in YpR situation. And it's possible to write this rate as the sum of lambda j of A when eta belongs to some set AG of A, and these sets AG of A will make a partition of X, and they depend on the subset of the range of the interaction for site A. And then there are some quantities here, lambda bar j, which is the difference between lambda j and lambda j minus 1, and lambda bar 0, which is lambda 0, and then the sum of this lambda bar 0 and the maximum value of the lambda bar j for j non-zero. So I wanted to show what it gives for a simple model, the T92 plus CPG. So you see, for instance, to become A, there are three cases. Either eta 0 is in Y and it's the rate V, or eta it is G and it wants to become A, and there is on -1 something which is not C, and then the rate is W, or on -1 we have C and the rate is W plus R. So you see that this partition AG of A is just the three sets here corresponding to the three possible values. Lambda J is V, W, and W plus R, and the lambda bar, which is the difference between one and the other. So here it's V, here it's W minus V, and here it's W plus R minus W, so it's R. And we do the same in the four cases. And so the minimal value is V, the maximal is W plus R, the range is 2, and then the lambda bar is the maximum between W minus V here and R, and the lambda bar 0 is the sum of the minimum is 4V. And then it's possible to put this in the generator to replace lambda J by lambda bar J plus lambda bar J plus -1 plus 1, I don't know. And then we get this form here for L1, which is the sum of two generators. First, a part with the lambda bar J for J different from 0. And then here we have lambda bar 0 of A over lambda 0, and then we multiply and divide by this lambda bar 0, which is non-zero because we did assume that M is positive. And so here you see that to have a change, you need tau x eta to belong to this set A L of eta, as we saw on the array before. But here, okay, no condition. You become A at a rate lambda bar 0 A over lambda 0. So that's the little improvement I showed you for the ergodicity conditions. If S minus 1 lambda bar is less than lambda bar 0, then we get exponential ergodicity. It's possible to do even better by cutting this generator in many parts according to the values. But okay, so I won't go into that. And then how do we represent the substitution? So as you saw before, as I told you, here there are two cases. Either we have to look at what's around the site where we are to decide to do the substitution or not. And here we always do the substitution. So this we'll see in the graphical representation. We'll have two types of marks. First, something called GA for J, which is not 0, and it's distributed according to a Poisson point process of rate lambda bar J of A. And then for the second part of the generator, we'll have independent Poisson point processes of rate lambda bar 0. Then if we consider discrete random variable with values ACTG, then with the probability lambda bar 0 of A over lambda bar 0, then we'll have the second type of mark, delta A. So what do we do on our graphical representation? In the first case, we look at what happens for eta ti minus 1. Either it belongs to at least one of the sets to x minus 1 AL of A larger than J, so that's what we have in the generator. Then we do the substitution. We put A on site X, like that, otherwise nothing. And for delta A, we see that we have no condition, so we always do the substitution to A. So I'll try to show you on a picture. I hope so. As is written here, and I try to remember, and you try to remember with me, that blue is A, green is T, gray is C, and red is J. Okay, so let's look at this picture here. So if we go from below, the first thing we meet is this 1C. So we are green. I already forgot what it means. So green means that we are T. So if we are T, we can become a C without looking at anything else. There's no R part here for our model. So here it will become C, no problem. So we are gray here. So the second point here is this 2A. So it's red meaning J. So it's 2A. So J wants to be an A. And so it means that we have to look to the left because it's YpR. So here it's gray. Is it possible? Yes, it's possible. So we turn to blue, which is A. Then we go up. We are here, 2T. And then I think it's not possible, but I don't remember why. Okay, 2T is blue and stays blue. So blue is A. And A cannot change to T. Okay, I don't remember why. So let's go back here. No, it cannot change to T here. It can change to T only in the first line, and that's not something that we consider with these marks. So it's not possible. So we just go up here, and then a delta, and a delta, you can become whatever you want. And then another delta, and you become whatever you want. So that was the representation for the substitution. And then for the cut and paste, we just do cycles. So for instance, if we go up, we have all the colors. Here we meet a cycle between 5 and 3. So those two are not concerned, so that go up. And it means that 5 goes to 3, and then the others are just pushed. So red comes here, blue comes here, and gray comes here. And we go up, and then it's 1, 4. So same thing. Green goes to 4, and then the others are pushed. Blue, red, red. And then we do the superposition of both. And the generalized dual is in the other way around. And the point is that, okay, we begin up and we have to go down. And what we want to know is where did we come from? So how much information do we need? So that's how we will look at things. So then we have a set, and this set will become bigger or smaller. And if we meet a GA mark, then it will become bigger because we need to know what's on the neighboring sites because of this YpR rule. So we need to add all the sites belonging to this range of interaction. But if we meet a delta A mark, since we did to go up, we did not need anything, we don't know we can do anything. So then we have just to put out the site X. And for the cycles, we just go the other way around. So that's a possibility. So we are here. And then, okay, we go down. First, I meet a delta. So nothing. There's nothing more. Then I meet another delta. Nothing more. Then I meet a cycle. And with a cycle, I do my cycle here. And I go down. I see a T, so I would have to look, T is YpR, I would have to look to the right. But okay, since here I have the two going down, I cannot say, but I do add a branch here. I do add something, even if I don't see it. It's there. Then again a cycle, so I cycle, and then again a 2 here, so I go to the left. So I add a small piece here. Then I see 1 C1, I don't have anything to add, so it's there. So I think that's it. I'm done.
Thank you so much. You can unmute and thank Ellen properly. Are there any questions or comment? So one thing that I didn't understand is if it's from this back one reading that you see that you get something that is not Markovian.
Yeah, because you have to look at too many. I mean,
it's not clear what to do.
It's not clear. Yeah, it's not clear. It's not clear at all.
And why?
Yeah.
No, but and why you don't have colors in when you go backward?
Because you go back, you don't want colors. I mean, you just want to construct this branching process, which I didn't construct, to get the ergodicity or non-ergodicity. You're not interested in colors anymore, but just as the number of branches you have.
Okay. So in a sense, you're aiming for
extension
for a different dual process.
Yeah.
It just counts the branching. Let's see.
So actually, I was interested in Pablo's, if Pablo knew more, because the paper is quite old that we used.
Then maybe there is a question, yeah, from Milton.
Yeah.
Mm-hmm.
So yeah, so I have I think maybe 2 questions. So the first question is about the mean field prediction. So in principle, the mean field prediction for this model, I mean, it will be a 4-dimensional ODE.
Mm-hmm.
And the question is whether your conditions imply that this 4-dimensional ODE has a unique attractor.
Mm-hmm. Yeah, so this we did not look at all. But I mean, in fact, we suspected that maybe there are no conditions at all. Maybe it's always ergodic. It's not so clear because what we did was we couldn't find any general method. So what you would suggest is first to look at the attractors to check.
Because if you have, let's say, a strange attractor in the field, that's an indication of non-ergodicity, no? Because there's not a at least there is no natural stabilization around the density.
Mm-hmm.
Yeah, so it's I mean it's not at all a criterion, but I think that physicists use it as
indication.
Yeah, as an indication. So without a lot of shame on doing that. The other question is that I don't know if you look, there is a paper by Avena and Fayonato about perturbations of Markov processes. So they take a Markov processes for which they know ergodicity and nice properties, and they perturb it superposing another dynamics, and they ask this question.
Okay, so no, I don't know. So can they answer? I mean, so I will look at it. Yeah.
Yeah, so they use it for random walks in random environments, so it's a completely different context. But the theorem they prove is completely general. It's about Markov processes, and if the conditions are satisfied, they are satisfied. So it's
okay. Well, thank you.
It's a sort of perturbative, so you always need the rho to be small. But on the other hand, it works without this type of attractiveness or duality conditions. So it might give you something different.
Okay, thank you.
Yeah. And so, well, I think that was basically my 2 questions or remarks.
Thank you. Let's see if there are more questions or comments.
Yeah, I could ask just a question.
Yes, please.
Nice talk, Ellen.
Thank you.
So I didn't quite follow the, how did you get the exponential rate of convergence?
Actually, you dominate it. You look at the number of branches you get. You dominate it by branching, and then you want the extension of the branching. So that's looking at the branching model. You get the exponential result.
Yes. And when something was equal, then you should get polynomial or something.
Yeah, yeah.
Okay, thank you very much.
Welcome.
Okay, so now that Sunde make that point, I remember another thing that I wanted to ask, if I may.
Please.
And it's about decay of correlation. So in this exponential ergodicity part, do you know that you have a spatial decay of correlations, or do you have some information about that?
No, not at all. Not at all.
Yeah, because in principle, no, it's from these branches, no. So basically, you want these branches to disappear quick, but then if they disappear quick, they also don't get too far, no.
Yeah.
So what it might be.
Let's see if there are no more comments or questions. No, I would say no. So thank you very much, Ellen.
Welcome.
And we
Thank you.
Thank you, Ellen.
update
Thank you,
next
Fabio.
week.
Merci, Hélène. À
Okay.
bientôt.
À bientôt.
À bientôt. Bye bye.
Ciao.
Ciao,
Bye.
ciao.
Bye.